So, Anaya, have you finished your Unit 2 quizzes, all the quizzes? And the test. Okay, good. So, I'm going to declare the result by tomorrow morning. Okay, children, effusions and diffusion. So, we are going to discuss about the meaning of the process. Oh, sorry. Yes. Yes, Anaya, I have to do that. I'm so sorry. Okay, I'll put the videos. So, what's the difference between effusion and diffusion? Effusion is going from very high pressure to low pressure. Gases, they move from high pressure to low pressure. This is the law of nature. Temperature, from high temperature to low temperature. Heat flows from high temperature to low temperature. Similarly for the gases, from high pressure to low pressure. Similarly for the concentration, you must have heard these words, osmosis. This is from high concentration to low concentration. So effusion is from high pressure to low pressure. To see these two containers A and B, in which case you can see the gas is effusing from high pressure to low pressure. In the B, this is effusion. You must know the difference between effusion and diffusion very clearly. And this one is diffusion. So what is diffusion? We have understood effusion, but what is diffusion? Diffusion is just intermixing of gases. Intermixing of gases. It's always happening all around you. Your mother is doing some cooking in the kitchen, she's baking a cake, and you can smell the cake in your room also. Everywhere the aroma is there. What is that? Diffusion. So, diffusion is taking place under normal conditions. It's just the intermixing of the particles, like these two gases, they are intermixing with each other. Because gases, they have kinetic energy, particles are moving, colliding with each other. So they start intermixing like perfume. When you spray perfume, you can smell it in complete room. So that is diffusion. So diffusion is intermixing of gases. Effusion is when the gas runs from high pressure to low pressure. You must have seen some gas cylinders. When we open a gas cylinder, you heard that voice, shh, kind of this. So that kind of gas coming out with force from a small nozzle like this. See here, from a small hole like this. That is effusion. So the gas is coming out with great force from a gas cylinder. When you open the knob, the gas comes out. That is effusion because that gas is coming out with great force because of the difference in pressure. But diffusion is simple intermixing of gases. Is it clear? Okay, now based on this effusion and diffusion, we are going to understand the this is the last law of the gas laws, Graham's law, which is based on kinetic energy and velocities. So children, we know that kinetic energy is 3 by 2 RT, which is 1 by 2 mu squared. This I'm taking as the molar mass. And you also know that this is the average kinetic energy. average. And this u is the root mean square velocity. So I'm going to rearrange this equation, this one. Kinetic energy is average. It's not of one molecule, it's the average of all the molecules. Molecules have different kinetic energies. We did the distribution curves. And u is the, I'm going to take it as RMS. I explained you the meaning of this RMS in the last class. Who is going to tell me the meaning of RMS? Units of RMS? Yes. Not the units, sorry, meaning. And what is the unit of this U? Unit. This U. Yeah, meter per second. But we are not going to work only with meter per second. For gases, in place of meter, you can take the volume also. How much volume of the gas has come out per unit time. So its units can be, for the gases can be meter per second. It can be milliliter per second or liter per second. So we'll do different questions in which we'll be using different units for the to measure, to compare the speed of two gases, to compare the rates of effusion and diffusion. So you will see that we are using different units for it. So now let's rearrange this equation. Can I say u squared is 3RT over m from these two? Then u is, which is root mean square velocity, is square root of 3RT over m. What is m here? It's the molar mass. I'm working for 1 mole. Amodita is here? Yeah. Mhm. Okay, this equation is very important. It's the outcome of these two. Now, let's see. If I give you a gas A, any gas A, I want to compare the speed of effusion or diffusion, diffusion. I'm going to use this Graham's law for both of them, for effusion as well as diffusion. If I want to compare the speed of effusion or diffusion of A and B by using this equation, speed of A is 3RT over MA square root. Speed of B is 3RT over MB square root. Let's say both the gases are at the same temperature. Temperature is same for both of them, A and B. Then what happens? Cancelled. R is constant, T is same. Yes. So what is there then? If I rearrange it properly, I'll get this MB over MA. This is your Graham's law. The ratio of the velocity or rate of effusion or diffusion, you can call it like this. The ratio of rate of effusion or diffusion of two gases is inversely proportional to the square root of their molar masses. If A is in the numerator, its molar mass is in the denominator. This is Graham's law. So according to Graham's law, the rate of effusion is inversely proportional to the square root of the molar mass. Is it okay? At constant temperature. So if the molar mass is high, what happens to the rate of effusion? Will be low. Speed of effusion, the way the gas is coming out, it will come out slowly, or diffusion will be slow. Okay, so effusion and diffusion, for both the processes, we are going to use the Graham's law. So according to Graham's law, the rate of effusion of gas A with that gas B is equal to square root of molar mass of, in the numerator, molar mass of B, denominator, molar mass of A. Good, Anaya. Children, I'm very happy to inform you that today was AP Chemistry Result Day in USA, and most of my students are 5 and 4. Most of them are 5, and I was really surprised to see, and I believe the test was very tough. And I'm very, very happy for my children. 4 and 5, that's the only result which I'm getting. And I'm sure that if you people are working very hard, I was telling admin that this time my summer group is really nice. You 4 are very hardworking, doing the quizzes regularly. Stay like that. And definitely you'll be 5. From my side, all 4 of you are 5. Okay, now, Amodita, are you done with the quizzes of Unit 2? Because I saw that you are still doing it. So can I declare the result of Unit 2? Amodita. Akash, you are done, right? Akash has already done Unit 2. Why? How much is left? Can you finish it fast? Oh, test is very simple. Can you do it today? I would like to declare the result tomorrow. And then we'll start working with the remaining part of the Unit 3. Okay, so the Graham's law is clear, children? So whoever is not done Unit 2 completely, please finish it today. Let me declare the result before next class. Okay, here is a very wonderful question. Let's try to do this question. In this experiment, this is an experiment. They are discussing the diffusion of ammonia and hydrochloric acid. During the experiment, they observed that they placed a cotton here, a cotton on one side of the tube, a cotton full of hydrochloric. In this, hydrochloric acid gas is there. So, and in this, ammonia is there. So, HCl gas is coming out of it. Ammonia is coming out of it. They are reacting ammonia with HCl, forming ammonium chloride. You can see it's a combination reaction, children. Combination, they are just combining. This reaction has many names. Combination reaction. It's a synthesis reaction. Synthesis. You're making one product. And it's also called as acid-base reaction. Acid-base. This is the acid. And this is the base. This topic we are going to do in detail in Unit 4. Okay, so ammonium chloride is formed. Ammonium chloride is not a gas. It's a solid. You can see here, solid. So here they observed formation of solid fumes. You can say fumes here. These are fumes. Fumes of which are visible to you as white solid. White in color, visible to us. So they observed that the fumes are formed here closer to HCl. The question is why? Why these fumes are not formed exactly in the center? Why they are formed more closer to HCl? Mhm. So Mayank is saying hydrochloric acid is slower than NH3. Why? Why is it so? Give the reason. What's the molar mass of HCl? Yes, the molar mass of HCl is 36.5 grams per mole. And ammonia is lighter gas. HCl is heavier gas. Ammonia will move faster than HCl. So by the time HCl has started moving, ammonia is already there. A fast moving car, a slow moving car. So understand the difference. Ammonia is moving like a fast car. It's moving very fast. By the time hydrochloric acid is out of the its house, ammonia is already there. And there they combine to form ammonium chloride. Okay, so can we do this question? Very simple. Okay, yes. A is the answer. Why? Because helium is lighter than neon. Yes. And another thing, amount of the gas, volume container, temperature, both the gases are at the same temperature. So they are not these factors we are not going to consider. Let's say here they have given zero point 0.5, zero point 0.5. If I say 2, 1, do you think this will affect the speed of the gases? The Graham's law has anything doing with the amount of the gas? No. Okay, so understand here for the Graham's law, we have only molar masses there. Temperature is also, we have to keep the temperature same. Okay, this one. So you're not changing A, you're not changing the temperature. What else you're not changing? It's a rigid tank. Volume is constant, temperature is constant. Then you have to see the relation between pressure and the moles. You're adding more gas, more gas. So when you increase the number of moles in a rigid container at constant temperature, what happens to pressure? Increases. So I don't think B is the answer. A and B are out. Is D out or yes? Start using elimination now. D is out, right? Because number of moles are changing. Is this E out or no? E is out. Because in the container, rigid container, initially these are the oxygen molecules. Then you are adding more, right? So the distance is decreasing. C is the right answer, and Akash is explaining us. Okay, so when we have these kind of confusing questions, then start using rule of elimination. Then you'll see just to check whether I'm right or wrong. So in the examination, just give a scan to the other options also and see why they are ruled out. Good. Akash is already explaining us. Okay, let's see this one. You are decreasing temperature. So the molar mass will decrease. Volume is constant, right? In a sealed container, constant volume. Akash is saying C and Mayank is saying Mayank and Amodita is saying E. Anaya, what do you think? It's a fixed container. Volume is fixed. When I put a gas in it, don't you think the molecules, the gases, they occupy whatever volume is available? So the volume of the container remains the same. So do you think the average distance between the molecules will decrease here? No, it's going to be the same because volume is not shrinking. Volume is still the same. It's a constant volume. So the average distance between the molecules is not changing. So what is changing? The average speed of the molecules. So what will happen to the speed? Kinetic energy is directly proportional to temperature. So as temperature decreases, kinetic energy decreases, speed decreases. So answer is Mank and Amudita. Anaya, you're there? Anaya. Okay. Check this one. STP. You know the STP condition? This is the amount of hydrogen gas. This is the amount of oxygen gas. So amounts are different. Molar masses are different. So what can be same? Very simple question, please answer fast. Yes, because temperature is same. Both the gases H2 and O2 are at the same temperature. What about their average molecular speed? Which one has higher speed? What about their volume? Which one has higher volume? Do you know their volumes? What's the volume of H2 gas? What's the volume of H2 gas? Can you tell me the volume? 22.4 divided by 2 liters. STP, 1 mole is 22.4 liter. Right? Hydrogen gas is this. O2 gas is 1 mole, so it's 22.4 liters. So remember this. At STP, 1 mole of gas is 22.4 liters. So if their moles are 1 is to 0.5, so their volumes are also. This one is doubled and this is your 11.2. This is the ratio of their volumes. 2 is to 1. Which one is going to have higher effusion rate? And which one is going to have higher density? Mayank, how come H2? Density is defined as mass per unit volume. So if you see 0.50 moles multiplied by nearly 2, volume is 11.2. This is the volume of the hydrogen gas. So can you calculate the density of oxygen? is 32 here, right? Just see the volume, density in both the cases. Which one has higher density? You have your calculator with you? And give the answer with the units. This one is 0.089 grams per liter. And what about this one? Anaya, second one? Definitely is greater. So, Mayank, you have understood this? Okay. So, as it is, we can see that oxygen is much higher in molar mass than hydrogen. Okay, let's do this question. This diagram is for N2. This is for N2. They are asking to make, on the top of this, they are asking you to make for O2. So let's make for O2 on the top of this at the same temperature as dashed line. So the graph will go in this direction or in this direction. O2 has more speed or less speed. It will go to the left and here, like this. O2 has less speed because of high molar mass. So graph will shift to the left. This one. This is wrong because it's starting from here, and to the right is wrong. Wrong. This is not the correct representation. Right? So this is the answer. The graph is shifting to the left because the speed of the O2 molecules is lesser than that of nitrogen. Let's do this one. Okay. Understand this question. In this question, there is a pinhole sized here, and in one container on one side, helium gas is there, argon gas is there, and neon gas is there. So they say when they make this pinhole sized leak from here, the gases will effuse, they will come in this. So they are saying that finally, which of the gas will have more partial pressure in this container? Or in this container, in this. Gases started effusing. So finally, in this container, which gas will have more higher partial pressure? Which gas will have less partial pressure? You know, partial pressure is proportional to the number of moles of that gas. We did this equation Pa equals to NaRT over V. So this one is not changing. So when effusion starts, which gases will effuse more? Which gas will effuse faster and more? Mhm. Helium. So more amount of helium will come. So what happens to the partial pressure of helium in this container? In this minimum. In this container, in this one, not in this. Let's say this is B, this is A. B is after effusion. So in A, what happens to the partial pressure of helium? Minimum. And which gas is effusing with the minimum rate? Which gas is effusing very slowly? Argon. So partial pressure of argon will be maximum. So what is the option here? A is the option. This is for container A. After effusion, helium will be minimum because it has a very high rate of effusion. So most of the gas will go in container B. Argon will be maximum in amount because it has the highest molar mass. So it is the one which is left more. Neon in between. Is this question clear? And in this container, in the B container, what should be the answer for the B container? Which gas has the highest pressure? Helium has the highest pressure and argon has the lowest pressure. In that case, okay, options are not here. So in that case, it will be like this. Pressure of argon less than that pressure of neon, which is less than pressure of helium. This is in B container after effusion. This is in A container before. This is also after effusion, but A is the original container from where the effusion has started. Is it okay? Okay, let's see this question. Remember, average speed has nothing doing with the pressure, nothing doing with the amount, nothing doing with the volume of the container because it is proportional to the temperature. Yes, it is related to the temperature. This one, 3RT over M. So the average speed, the root mean square velocity, is related to molar mass and is related to temperature. So which container has the highest temperature and the lowest molar mass? That's the answer. Akash, you are there? So please do not get worried about these pressures or this volume. They can give you any volume. It can be 2 liters, it can be 10 liters. You have to simply compare the temperature and the molar mass and pick up your answer. Okay, check this one. When you are reading the question, underline the important information. Temperature is same. So when you combine the gases, 1 liter of this, 1 liter of this, temperature is not changing. If temperature is not changing, what about A? That's wrong. Oh, D is the answer? Okay. Yeah. These are so easy questions. D is the answer. Good. Akash, you are not giving answers. Let's see this one. So when these distribution curves are there, please pay attention to this axis. Sometimes kinetic energy is written. It can be kinetic energy also. Or sometimes it's for the speed. So you have to be careful with that. So it's a molecular speed. D is the answer. Okay. So which gas is heaviest? If I put them like A, B, C, D, which gas is heaviest? A is heaviest. Then how come their kinetic energy is same? They all are at the same temperature. See? Yeah. So kinetic energy is same. But you said this is heavier, and we know that kinetic energy is 1 by 2 mu squared. Molar mass is different. So how come kinetic energy is same? Anyone? Yes, because when the molar mass is more, then accordingly speed will be less. So the product remains the same. So this product is same for all these gases. That is the reason. Okay, this one. Oh, this is so simple. Very fast answer is needed. Mayank, how come C? Amodita, how come C, Mayank? Temperature is same. So when they are talking about the average kinetic energy, please pay attention to temperature. Right, Mayank? When they are talking about the speed, then you compare the molar masses. Mayank, kinetic energy is directly proportional to temperature. Nothing doing with molar mass. This equation, remember this equation? Do you have molar mass here? No, just temperature. If temperature is same, kinetic energy is same. Is it clear? So don't look at the molar mass. You're comparing average kinetic energy. If I say speed, average speed, then what's the answer? If I say average speed, then A is the answer. Yeah, good. Make a difference here, okay? Kinetic energy, check for temperature. Speed, check for molar masses. Okay, this is the same question which we did with ammonia and hydrochloric acid. So read the question. In this, there is an acid. In this, there is a base. Acid and base, they react to give you combination reaction to give you a solid. I can give you what is the product here. This hydrogen will go over here. So this is CH3, NH3Cl. An ionic salt is formed. This we have already done. Is NH4Cl minus. Can you tell me what is this then? Just look at these two. I'm just transferring hydrogen from acid to this nitrogen. CH3, NH3 plus Br minus, right? So make this product. Give me this product, children. And you started answering. Yes, Anaya, very good. NH4 plus, all these are solids. So they are saying which one will be more closer to the center. So they should be nearly of the same molar masses. They should be nearly of the same molar masses. You see, this one is out completely. This is very heavy. It's 81 something. This is 17. This one already out. We did one example based on this. This is 36.5 and this is 17. We have to compare C and A. So what is the molar mass of CH3NH2? HCl is 36.5. CH3NH2 is how much? 31.05. HBr is somewhere 81. I'm just taking approximate. And this one is again 31.05. So definitely in this case, it will be more in the center because these are comparable molar masses. In this case, it will be more closer to, yes, here. Okay. In this, it will be closer to, in this, we have already done, in this, it will be closer to, yeah, like this. So this is a very popular question. Okay, let's see this one. temperature is held constant. When the temperature is constant, all these questions, all these answers have average kinetic energy. No, no, that's the answer. And they're asking for the average kinetic energy. So, what effect do the volume and pressure changes have? Nothing, no effect. Volume, pressure, amount, they cannot change the average kinetic energy. Only temperature can change it, right? Mink, you're understanding? Okay, let's do this question. You have to make for helium on the top of this hydrogen. You have to make for helium. So it will be to the left side or right side? This is speed. It will be to the left side. So like this. So height will increase, right? So what's the answer? A is the answer. Okay, check this. Mhm. Average speed will be greatest in helium container because that is the one with minimum molar mass. But how can I compare these three? Because they have not given anything about it. Can you see these two? And the pressures are nearly same. Temperature is same. Let's take they're in identical volume is same. So these two gases have same volume, same pressure, and same temperature. Pressure is same. So don't you think that the amount, the moles will be same and must be same? So what can I predict from this information? Which gas is more heavier, 3 or 4? Moles are same. Yeah, so definitely 3 is, yeah, 4 is more heavier than 3. But here helium is very light, so answer is without doing all these things, we can just compare it like this. Fast answer, please. Yes. As you lower the temperature, what happens to the speed? Speed decreases. The graph will go like this. Okay, so that's the end of your kinetic molecular theory. And now I'm starting the new topic from unit 3 only. Sharing is presentation. This topic is very simple but very interesting. It's about solutions, making of the solutions, and it's about solubility rules, solubility, hydration, and then questions based on it. So, what do you know about the solution? What's the meaning of the solution? Somebody asks you that, okay, you're learning chemistry. What do you know about solution? How can you identify a solution? First of all, a solution is a mixture of two or more than two components. Yes. Second, this mixture has to be homogeneous. Only then you can call it a solution. Okay, so solution is a homogeneous mixture. This is very important line. So what do you think? Air. Air is a solution? Yes or no? Air is a solution. Remember we did alloys. Do you think they are solutions like brass, steel? Are they solution? Do you think they are homogeneous mixture of two or more than two metals? Yes, they are solutions. They are homogeneous alloys. When you look at a steel, can you see there is chromium, iron? Can you see those particles? No. It's a homogeneous mixture of iron, chromium, carbon, nickel. Remember we did in unit 2. So it's not necessary that when I say solution, it has to be some liquid solution. No, it can be gas in gas. See, gas in gas, air. In air, which is a solution, homogeneous solution, we have two components. One, solute. Every solution, every solution has two components. Other, solvent. Solvent is in, solvent is in excess. Solute is in less amount, less amount. This is very important, children. Please write down, in place of air, you write solution here. I'm telling you one important thing. In the solution, the physical properties are governed by solvent. Physical properties. What are physical properties? Can you name some physical properties? Okay, more? Anaya, more. Okay, more. Mhm. Melting point, boiling point, delta H of fusion, vaporization. These are physical properties. If I make a solution in water, then the boiling point be somewhere closer to 100. Not exactly 100 because of the impurity. There is always some elevation in boiling point, which you can learn in chemistry Olympiad, but not AP chemistry has deleted this topic. But otherwise, if you take a solution, the solvent is going to govern the way Anaya said color, texture. If it is solvent is a liquid, your solution is a liquid. If solvent is a gas, your solution is a gas. Okay, can you put it in the direct chat, Akash? Because I cannot answer like this. This in the journal chat. You're giving me a message in the direct chat. Can you transfer it to the journal chat? Are you doing this quiz right now? You're not learning this part? Can you just share it there in the journal chat, Akash? Which everybody can see it then. Okay. Yeah, that's the right answer. Okay, flag this question, Akash. So when you feel something like that, please flag the question. No, no, I think there is some error then. Okay, Akash, can you flag the questions which you feel that are not right? Okay, thank you. I'll check that. Okay, once you submit the test, then I'll check that. Now, right now, please pay attention here. So, solvent physical properties are governed by the solvent, and chemical properties are governed by the solute. This is very important point. Okay, now if there is a gas with gas, here is the example. Gas in liquid, you know that fizzy drinks, soft drinks, when you are drinking this different types of soda based drinks, right? So they all are gas in liquid. Liquid is water and gas is soda. That's CO2, CO2 gas. So what is soda water? CO2 in water. Gas and solid. Can you give me example of gas and solid from daily life? Gas and solid. For gas and liquid, bubbles, air bubbles, when you are using shampoo and all these, then you can see that how that bubbles are formed. That is the example of gas liquid. Gas and solid, you have seen forms. They are very spongy sponges. They have they are very porous. So what is there? You can squeeze them. When you're squeezing them, air is coming out. Yes, yes, cake. Cake batter. Batter is semi-solid, but cake is also spongy cake. You press the cake, any solid. When you press the solid, if it squeezes, then you say gas and solid. There is gas inside it, right? Liquid, there are plenty of them. Sugar in, sorry, not sugar. This drinking alcohol in water. Ethanol is drinking alcohol. Liquid in liquid, we are making many of them. We are making different types of cocktails. You are mixing different types of liquids. Solid in liquid, plenty of examples. And solid, alloys. Best example. Metals mixed with metals like brass and solder, and then steel also we did. Steel. Okay, and solid and liquid, sugar in water, salt in water. So there are plenty of them. They should be homogeneous. They should be soluble into each other. Now, how to make standard solutions in the lab? First of all, understand the word standard solution. Standard solutions mean anyone? A solution whose molarity is known to us. Molarity is known to us. What is molarity? Molarity is concentration. If you know the concentration in terms of molarity, then we call it as standard solutions. So in the lab, they will ask you to make many standard solutions. This is one of the, I don't know, after every 1 year, they post a question like this in the AP exam. Explain all the steps for making standard solutions with minimum error. This is one of the, like from last 2, 3 years, I have seen this question either in the form of multiple choice or free response. So please pay attention to this part. It's always there. It's a very important question. Let's say I want to make standard solution of NaOH. Your teacher is saying make a standard solution of NaOH. NaOH is solid under normal condition. And she is asking us to make 0.5 molar. And she's saying don't make more than 250 ml. So this is the information she has given us. She's asking us to make 0.5 molar NaOH 250 ml. So how to make this solution? From the molarity, I know that molarity is moles over volume. Volume has to be in liters. Volume has to be in liters. So from this information, I can work out the moles. Moles equals to molarity times volume in liters. which Akash is already giving us. Yes, take care of sig fig here. So I'm placing zeros. 0.125 moles. Can you convert these moles into, you cannot measure these moles in the lab, right? So you have to convert these moles into grams of NaOH. This is mathematical part. Take care of the significant figures. So 0.125 moles and the molar mass of the NaOH is 40 grams, 40.01 grams, something like that per mole. And the answer is, Akash is giving me something else. Make, who is right? Mank is right. Akash, check your calculations. So I'm going for three significant figures, right? Three significant figures are very important here. This is the first you are going to do this mathematics calculations. So whenever they ask you to make a standard solution, what is the first thing? Pick up your calculator and calculate the mass of the substance which we need to weigh. So you have seen this information is there and I calculated the mass here. So this is the mass of the NaOH which I can measure. I cannot measure moles, so I have to come out of the moles. I cannot measure moles. I can measure mass. What else I have to measure? Volume. This also I can measure. Now, okay, it's not 0.5, it's 5.00. This is the answer. Anaya? 5.00. Okay, so this part, calculation part is clear. Now let's come over here. How to make, this is the question. They ask you to explain the steps. So what is the first step? Weigh 5.00 grams of NaOH. What is the second step? Dissolve, make a homogeneous solution, dissolve in minimum amount of water, right? Third step, this is the apparatus which we are going to use. It's very, very accurate with very high significant figures. We call it as volumetric flask. Volumetric means volume measuring flask. It's also called as round bottom. It has a round bottom here. Round bottom volumetric flask. This has very high accuracy. It has only one mark on it. One mark. There's no marking. No more marking. And this I'm going to take. How much volume you want? 250. So I'll take 250. In the lab, you have different volumes of the volumetric flask. 50, 100, 200, 250, 500, 1 liter, like this. So please know this apparatus. Now you're going to put this solution here in this. Add it. Okay. Now clean, just because you made the solution here, so you have to rinse it. This is rinsing. Rinsing means that once you pour all the solution, then add more water to remove if any NaOH is still sticking here. To remove everything, the last part of the NaOH should come here. So rinsing with water. Now add more water. Add water. As you add water, stop here. Can you see the mark is here? Stop here. Then use a dropper to reach the mark. Mark is here. This is the mark. So to reach up to the mark, use dropper. And your eye should be here. Means you should be holding this flask in your hand and this mark should be at your eye level. And then very carefully you're adding in drops the water, and once it will reach up to this mark, then your solution is made. Then shake it. Shaking is important. Shake it properly so that it becomes a uniform, homogeneous mixture. Is it clear? Can I give you one question? Okay. So very first thing is weighing. Then making a homogeneous solution in minimum amount of water. Then selecting a volumetric flask and pouring the solution, this homogeneous solution, into this volumetric flask. Then rinsing this beaker with more water to remove all traces of NaOH from here. Then add more water, come up to this level. Then use a stopper to come to the level very accurately. Your flask should be in your hand and the level of your eye and the mark should be same. Then you start adding with the help of dropper. Then you have to shake it so that it becomes uniform. Okay, make a solution 1 molar and 500 ml of which solution should I give you? NaCl. Ready? So first, calculate the moles of NaCl. How many moles of NaCl? So I want you to use this equation that moles equals to molarity times volume. Volume has to be in liters. So how many moles? 0.5 moles. Yes. I'm placing a decimal here. I'm making it as, because when we are dealing with standard solutions, sig figs are very high. So 3 sig fig. Then you convert this into grams. Yes, Amodita, how many grams? 29.2 grams. Now, what is the first step? You are going to weigh 29 grams, 29.2 grams of NaCl. Yes. Then you're going to pour it in a beaker. You're going to put it in a beaker and make a solution, clear solution, right? Then you're going to select volumetric flask. Type this word volumetric flask, because if you don't speak, don't type, you'll forget the word. Yes, the way Anaya is typing, volumetric flask of 500 ml. This should be 500 ml. Then you're going to pour your solution into this volumetric flask. What is this step? What is it called as? Rinsing. Rinsing means, like you must have seen that when your mother is doing something in the kitchen, sometime if something is sticking, then she puts some water, stir it, and she's adding back into the stock of the solution. Rinsing is done to remove all traces of the solute, NaCl, from this beaker. Very carefully you have to do, otherwise you'll end up with the error. Okay, so after that, add more water. Then stop closer to the mark. Don't go up to the mark. And then use a dropper. Your eyes should be fixed on the mark. Use a dropper and very slowly, drop by drop, reach up to the mark. Shake it and your solution is ready. Is it okay? And you know the molarity of this solution. What is the molarity of this solution? It is 1 molar NaCl. Even if you take a drop of this solution, you take 1 drop of this solution. If I say, okay, I have taken 20 ml out of it, can you tell me what is the molarity of this 20 ml? 1 molar. Yes, remember that. Moles will change, amount will change because the volume is less, but molarity will not change because molarity is moles per volume. You take 10 ml, you take 1 drop, you take 20 drops, molarity will be 1 molar. Moles will be different, amount will become different. Okay, now let's see the dilution law. I'm making a concentrated solution. My teacher has given me a very concentrated solution. Concentrated means molarity is very high. 16 molar sulfuric acid. She has given me this. We call it as fuming. If you open the cap of this solution, sulfuric acid is fuming, coming out as fumes, very, very concentrated. One single drop on your skin will burn the skin. It's so concentrated. But it's there in the labs, though it's not given to the children because teachers are handling it on their own. But how come they are using this solution? They are not using this solution, they are diluting it. Dilution means adding water. Adding water. Now, how to dilute a 16 molar, such a highly concentrated acid solution? How to dilute that? So, first of all, very first important thing which you have to understand that when you go from concentrated to diluted, you are adding water. And as you add water, what happens to the molarity? Volume is changing, right? So as we are adding water, volume increases. Molarity, molarity, yes. On adding water, as volume decreases. But if let's say I've given you the concentrated solution 16 molar, 20 ml. This is the volume my teacher has given me, and she's saying, okay, Uma, dilute it to 0.1 molar. She's asking me this. 16 molar to 0.1 molar, and she has given me 20 ml of this solution. She's saying take this 20 ml, 16 molar, and you dilute it to 0.1 molar. So this 16 and 20, when I multiply, let's say this is M1V1, when I multiply, what is this M1V1? Isn't it moles? And when I add water, I'm just adding water, nothing else. So the moles will remain the same. Moles will not change. Number of moles are not changing. So my M1V1, after adding water, M1 decreases, V1 increases, I'm getting M2V2, but the moles before dilution and the moles after dilution, they are equal. What Amodita is writing, please understand this equation. This equation is valid when moles are not undergoing change. When I'm adding water, moles before dilution, which is M1V1, And moles after dilution, they should be same. That's why we are saying M1 V1 is M2 V2. What is M1 in my case? 16. What is V1? 20. I'm going to take 20 ml. I'm not going to change the unit because it's a ratio. M2, M2 she has given 0.1 molar. She's saying make it 0.1 molar. V2 I can calculate. Can you tell me what is V2? 3200 ml means I have to make a volume of 3200 ml, or I can say 3.2 liters, right? 3.20 liters. This is mathematics. Now, what's the procedure? How to do it? The procedure is different. So first I will, because 3.20 liter solution I have to make, so I don't have any volumetric flask for that. I can use a graduated cylinder, like these kind of graduated cylinders. They have marks on them. So I can use that. So what we have to do, first you have to tell me that this is the total volume. So how much water we need to add? 20 is already there. So how much water is needed? Water needed, H2O needed is 3200. Yes, Akash, minus 20. Please take care of this. 20 is already there. This is the total volume finally. So it is 31.3180 ml. So how much water I have to add? How much water? 3.18 liters, right? Liters, Anaya. Okay, so now this is one thing, mathematics. Now understand the chemistry now. This is fuming, very concentrated. So when anything is given to you in concentrated form, as a precaution, we never add that concentrated all together in bulk. We add it drop by drop. Means if this is my graduated cylinder and this is the mark here, 3.20. So I'll put the mark here. Okay, I have to make a solution up to here. So what I'm going to do, I'll add water first. Let's say up to here, water. Up to any level, less than this, H2. Add water because it's dilute. Take it in bulk. Now take your this 20 ml and add it drop by drop into this water. Keep stirring because this is very concentrated and it can make the solution, because solution making will be highly exothermic. So it can make the solution jump out on you. So keep adding drop by drop, keep stirring the solution so that he should not get concentrated at one point. Solution should not bump out. And then finally, once you have added all the 20 ml, add more water, reach up to closest level. Start using your dropper the way we were doing earlier. Use a dropper and reach up to this level. Shake it properly and your solution is made. This is dilution law. Okay, so who is going to explain me dilution law here? What happens during dilution? Number of moles are, yes, molarity decreasing, volume increasing. What about the moles? Number of moles. Number of moles are Constant. Remember this. This can be multiple choice question. And this is the dilution law. Ready for some questions? Yes, let's do this. That's a really interesting question. These are the questions of AP and your chemistry Olympiad type. So first of all, MgCl2 is going to dissociate completely to give you this, agreed? So initially you have taken 0.20 moles, before dissociation 0, 0. Finally, this is 0. This is 0.20. How much is this? 0.40. Okay, Akash, you have to tell me the steps. Can you work out with NaCl now? What is the other one? KCl. So KCl will give you how many moles of Cl minus? KCl will give you same number, right? So what are the total moles of Cl minus? Total moles. Total moles are 0.50. And what is the total volume in liters? Volume in liters is 0.500 liters. So what's the molarity of Cl minus? Molarity of Cl minus, which I'm going to represent as square bracket. See this square bracket? This means molarity, concentration, is the moles 0.50 divided by 0.500. So answer is E. So Akash, you said E earlier? Yeah, good. Good. So when you are answering, Akash, give me the steps. You can be faster than me. Okay. So this question is very important. These type of questions, very, very important for chemistry Olympiad in AP chemistry. Question 2. Milligrams are given. Molar mass is given. So you know the moles. Milliliter is given. What's the molarity of aspirin in 50 ml sample? Whatever is there in 200, same in 50 ml, right? I want to introduce you with another equation. Use that one. We said molarity is moles over volume in liters. We are using this. But the same molarity we can calculate in place of moles, I can take millimoles. Millimole over volume in milliliter, because both of them they get converted by a factor of 1000. Moles to millimoles, factor of 1000. Liter to milliliter, factor of 1000. 1000 cancelled. But the question is how to calculate millimoles. Please pay attention, I'm teaching you something new. How to calculate millimoles? Millimoles is equal to milligram over molar mass. This molar mass 180. Just take it as 180 milligram per millimole. Molar mass. Molar mass, which I'm writing capital A, M, is defined as grams per mole, but the same value is valid for milligram per millimole. Then you need not to convert your milligram to gram. You just take this 360, divide by this 180. How much is this? 2. These are 2 millimoles. 2 millimoles divided by, don't convert this volume, just take it as 200 ml. Don't convert to liters, millimoles over milliliter. You'll get the molarity. How much we are getting? 0. Yes. So can you see that I didn't convert my milligram to grams? I didn't convert my moles, millimoles to moles, milliliter to liter. I avoided all these 10 raised to a minus 3 the way Akash is doing. Akash, am I right? Can you try this method, Akash? Because this is going to help us. Milligram, millimole, molarity can be calculated as millimoles over volume in milliliter. Unit 8, where we are going to do titrations. There you'll be doing so many calculations, and every time volume is in milliliter there. Every time. So it's better to work there with millimoles. Okay, so yes. Question 3. Amodita and Anaya, your answers are slow. So I'm giving you one more equation, children. We have done this equation that molarity is millimoles over volume in milliliter. Rearrange this equation. So millimoles are equal to molarity times volume in milliliter. Use this. Use this milliliter and molarity to get the millimoles of OH minus from this compound. Use this milliliter and molarity to get the millimoles of OH minus from KOH. Add them. You'll get the total millimoles of OH minus. Divide by total volume 60 plus 40 is 100. Ready? So how many millimoles from BaOH twice? From this. How many? You know that is going to split to give you 2OH minus. Ba2 plus 2OH minus. So 0.15 multiplied by 60 multiplied by 2. So it is 0.15 times 60.0 multiplied by 2. 18 millimoles, okay. Anaya is giving me 18 millimoles for this part. Then calculate Anaya for this KOH. Just multiply these two. Because 1 KOH is giving you 1 OH minus. 10. Okay, 10. So 18 plus 10 is 28. 28 divided by total volume is 60 plus 40. 100. So answer is, can you see that I avoided all these conversions to moles to liters? Because then mathematically it becomes slightly slow. Every time you have to type 10 raised to a minus 3, 10 raised to a minus 3, like this. So you can avoid that. You should come in the habit of using this equation also. Question 4. Akash, is it okay? You are there? Okay. Do this one. Again milliliter. But here this one is given to you in grams. You are going to get what? You can get moles. Then convert this milliliter to liter because you are getting moles, right? This is in grams. So why should I convert grams to milligram? This is the case when milligram is given. Right now it's in grams. So what's the molarity? What's the answer? Very simple question. Get the moles divided by volume in liters. Yes, D. Amodita is saying C. Amodita, check your answer. Oh, yes. See, sig fix. Sig fix is the problem. 60.00 250.0, both of them have 4 sig fig. So this cannot be the answer. Answer is this. Very good, Akash. Perfect. So take care of sig fig, children. You'll be tested for it. Next question. There are plenty of them. This one is simple. This one. So I'm leaving this question. You can do it because just mathematics. Let's do this one. So you can work with millimoles here. How many moles? They're asking moles. So get the millimoles first. So how many millimoles of Na3PO4? It will be 100 times 0.1 molarity times volume. That is 10. Then how many of Na plus are there? Now Na3PO4 will give you 3, right? So how many millimoles of Na plus? 3 times 10. Then convert that into moles because they're asking moles. So 3 times 10 times 10 raised to a minus 3. So answer is C. And take care of significant figures. Is it okay? Are we getting C here? Yeah. Okay. These questions are really, really very good questions. Can we do this? This is making of the standard solution. We want to prepare a standard solution, 100 ml, which should have a concentration of Cl minus this much. So from this information, can you get the millimoles of Cl minus? Then can you get the millimoles of CaCl2? And then you can get the moles of CaCl2 and then grams of CaCl2. Can we do this? Like this? This is the planning. Can we do it in dimensional form? One single line. Yes, children. Tell me, what should I plug in first to get the millimoles of Cl minus? Volume is given, molarity is given. Yes. So I will start with 100 ml times 0.100. This will be the millimoles of Cl minus. Now how to convert this into millimoles of CaCl2? What ratio? What ratio? 1 millimole of CaCl2 gives us 2 millimoles of Cl minus. Next ratio. I want to convert millimoles to moles because finally I have to get the grams. So I know that 1 mole of CaCl2 over 1000. Now I want to know the grams. Molar mass is given in the question. So 111 grams per mole. Get the answer with correct significant figures. The sig figs here are, actually there should be a decimal here. Go for 3 because all numbers have 3. So answer is, okay. Mayank and Amodita are saying A. Yeah, okay. Then this is confirmed. A is the answer. Okay, moving on. Yeah, this is the last question. Let's do it. So here volume is given in milliliter. Molarity. Molarity is also called as molar. Capital M is the symbol. Molarity, molar means moles per liter. This is molarity. So don't you think that you know the millimoles of this Na2CO3? You know the millimoles of this NaSCO3? Can you tell me what are the total millimoles of Na plus? Yes, total millimoles. Anaya, is this for this one? 450? Is 2 times 70 times 3.0 plus 30 times 1. Okay, yeah. Anaya is right. Very fast answer, Anaya. 450 millimoles. Mayank, Akash, you are also right. Mayank, you are understanding these questions? Mayank, mathematically, are you okay with this? Mayank. Okay, so millimoles of Na plus are 450. Good. Volume is, what's the total volume? V total is 100. What's the concentration of Na plus? 450 over 100. Answer is, Mayank, if you are feeling anything troubling you, please do ask questions. I hope you are understanding how I'm calculating the concentration of ions in the solution. Very important concept for your chemistry Olympiad. Okay, so that's the end of the dilution, making of the solution, standard solutions. These are the questions. Practice more questions from the website. Now, this is very important concept 3.8 and 3.10. So today we have done 3.7 completely. Now 3.8 and 3.10 is also simple, very simple, hardly any mathematics, but very interesting. Here you're going to learn like dissolves like. This rule, this is the universal rule. You know that I was talking about the solution, I was saying it's a homogeneous mixture. What is the meaning of homogeneous? Means should be soluble into each other. But do you think all compounds are soluble into each other? No. Some are soluble, some are not soluble. How to identify which one is soluble and which one is not soluble? What is the chemistry behind it? That some compounds are soluble into each other, some are not. For example, yes, Mayank is already telling you the meaning of like dissolves like. He said like here means similar IMF. The molecule is polar. Polar is soluble in polar. Non-polar is soluble in non-polar. Check this pentane. Is it polar or non-polar? Pentane. Mhm. This one. C5, H12. All hydrocarbons are. Remember, I told you this line. All hydrocarbons are whenever we have only carbon and hydrogen. Yes, Ananya, Akash. All hydrocarbons are. Yes, because the difference in electronegativity is very less. This is 2.5, this is 2.1. The difference is near about 0.4. Unit 2, quiz 2.1, 2.1, 2.2. So all hydrocarbons are non-polar. This line I have told you many times. So please, all of you, type this line here. All hydrocarbons are non-polar because we are not going to waste time in the exam to think about it. It should be settled down. Write the complete line, Amodita. All hydrocarbons are non-polar. Amodita and Mayank. Waiting for your answer here. It's a very important line. Amodita? Yes, good. Are non-polar all hydrocarbons? Please remember this line. And the reason? The difference in electronegativity of the chemical bond is very less. The bond is not polar. So definitely molecule is not polar. Okay, here this is pentene, non-polar, non-polar. So what are the IMFs here in pentene? LDF. Heptene, see this molecule? LDF. Do you think pentane and heptane are soluble into each other? Okay, now let's see the energetics. I'm explaining you why. Why these are soluble into each other. See the reason. When I want to dissolve pentene in heptane, sorry, pentane and heptane, when I want to dissolve them, the very first thing we have to break these attractive forces. Correct? So you need energy for it. Plus, you're breaking this. So you're breaking the attractive forces of the pentene, you're breaking the attractive forces of the heptane. That is also plus. It's endothermic. Breaking attractive forces is endothermic. You know that, right? But when we mix heptene and pentene, then new attractive forces are formed. These are formed, which is negative, exothermic. They say if the amount of energy needed to break the attractions and the amount of energy released when new attractions are made, if they are compatible, then solution will be made. If they are not compatible, then solution will not be made. Like for example, if the amount of energy needed, I'm just giving you a random example. Here this is 20, here this is 20. And the amount of energy released is near about 40 or 50. It need not to be very, very accurate. I will say compatible. I'll say yes. Here, the attractive forces can be broken easily because energy released can compensate it. Just like money, I have $200 and I'm in the market and I like something which is of $600. Do you think I can purchase it? No. So I can purchase something closer to 200, not of 600. Same here. So the coin in the nature is energy. Energy is the coin. If the energy needed to break this attraction is more, then the energy released when these attractions are formed is less, then no solution making. This is called as energetics of the solutions. Are we clear about it? Is it okay? Okay, see here, water, very strong hydrogen bonding. Ethanol, OH here, hydrogen bonding. When you put water and ethanol together, can you see new hydrogen bonding? So the amount of energy needed to break these hydrogen bondings, the amount of energy released when new hydrogen bondings are formed is nearly same. So yes, solution will be made. Check here. This molecule is very polar, very, very polar. Who is going to tell me why it is polar? It's very polar, tetrahedral. Chloroform is tetrahedral. Yes, it's not symmetrical. So dipoles are not cancelled out. Very polar because of these three chlorines, very polar. So the attractive forces are very strong. You need large amount of energy to break this. You need large amount of energy to break attractive forces from here. This is also polar. This is also polar. The new attractive forces are also very strong. Polar with polar, dipole, dipole. Very strong attractive forces. So the energy needed to break, energy released are nearly same. So are we clear about like dissolves like? Let's see the microscopic picture. I'm not going to help you in this. You are going to explain these interactions. So this is solution making, children. Pictorial representation of solution making. This is the solvent. Is this solvent liquid or solid? So what is the step one? Endothermic, exothermic. Step one. See the change. So positive, endothermic positive. Now this is solute. Is it solid, liquid? What is step one? This is a latex. Remember we did Born-Haber cycle for ionic compounds. What is step one? Endo, exo. Can I call this energy delta H2 as latex? You're breaking a latex. You're taking a solid and breaking it apart. Now these are gaseous. Gaseous. Totally separated from each other. These are also gaseous. What is step three? Amudita, which one is negative? This one, latex is negative? This one? No. What are you doing? You're breaking the latex or you're making the latex? What is happening? Latex can be negative, latex can be positive. It depends what you are doing. You're breaking it, you're breaking attraction. So it is positive. Right, Amudita? Right now it is positive, you're breaking. Okay, now what happens here? Attractions are made or attractions are broken? Not bonds, Akash, no bonds are formed. Attractions. There is no chemical reaction. Okay, solution making. So this is called as hydration. Like if this is water, then this is called as hydration step. Hydration. This is negative. You know what is delta H solution? What is the overall finally the solution making can be endothermic, it can be exothermic. Delta H solution is delta H1, the energy needed here, plus delta H2, the energy needed here, this positive, minus delta H3, the energy released here. This is delta H of solution. Now, I already know what is delta H2. If it is an ionic solid, then I can say delta H solution is delta H1 plus delta H latex minus, I know this, what is this called as? This is, if your solution is water, this is called as delta H hydration. You're understanding this, children? These terms are very important, latex, hydration. Now this delta H1, that's separation of the solvent particle and then mixing, it's going to be taken care because solvent is in excess. So when you separate them, when you mix them with the solid, the solute, then the amount of energy needed to separate and the amount of energy released when they come closer again, they cancelled out. So we are not going to consider this. So what is delta S solution, children? Write down this equation. This one. Am I right? So it means solution making can be exothermic, can be endothermic. Agreed? So in which scenario solution making is exothermic? Just compare these two energies. In which scenarios? When delta H latex is less than delta H hydration. That's what Akash is trying to say. Menk, you are getting this? This delta H solution is negative, exothermic. So during solution making, heat will be generated. When you are making the solution, you touch your container in which the beaker, the test tube in which you are making the solution, you can feel that the beaker or the test tube is now warmer. It will become warm. Heat is generated. And when it can be endothermic, delta S solution, endothermic, when, yes, please, all of you type. Yes, Anaya, very good. Amodita? Yes, good. So solution making can be endothermic, solution making can be exothermic. It's very rare when delta S solution is zero. You cannot have lattice enthalpy and hydrogen enthalpies exactly same. I don't think. It can be closer to zero for ideal solutions. Closer to zero. Write down this word though you will not test it for it. Ideal solution. You know, ideal gas law. What is ideal solution? Where delta S solution is nearly zero. We call it as ideal solution. In that case, energy needed to break the latex, and during hydration, the amount of energy released is same. Means the attractive force is broken and the attractive forces formed are nearly same. That is ideal solution. You'll not be tested for this word for AP chemistry. So we are good with the solution making. Okay, this is energetics of the solution, which I have already explained you. Delta H1, delta H2, delta H3. These are positive, positive. This one is negative. When you add all of them, it becomes delta H solution. You ignore delta H1, then delta H2, delta H3, it's the lattice and the hydration. We have already done this. Okay. This is the diagram of the solubility. We call it as hydration process. Why this hydration is exothermic? Hydration means your solvent is, yes, please answer this. Hydration means solvent is, yes, children, you are listening? Hydration. No, no. What is the solvent for hydration, Akash? If I say hydration, the solvent is, yes, water. Amadita, yes. Hydration is making a solution in water. Akash and Mayank, you're okay with this hydration word? Okay, what is happening here? This is water. This is NaCl. Can you see? This water is colliding with the solid NaCl. Colliding. Water is colliding. You see? When it is colliding, it's going to exert a force and this Na plus. Can you see how this Na plus is taken out? What is this? What is this? This is hydrated Na plus. Hydrated Na plus. You can write it like this. Na plus aqueous. What happened to Na plus? It is surrounded by, yes, Akash, you're right. It is surrounded by oxygen of the water. You already know that in water, oxygen is delta minus, hydrogen is delta plus. So can you see that how this Na plus is making very strong interaction with the dipole of the water? So what kind of attraction this is called as, children? Remember the name? We did this earlier also. Yes, Mayank is right. Ion dipole. This is ion and this is dipole. Very strong interaction. And you know, each Na plus will get surrounded by 6 water molecules like this. OH2, 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 OH2. How many I have made? 5. One more. Each Na plus is surrounded by oxygen of the 6 water molecule like this. And very strong ion dipole interactions are there. Similarly, Cl minus, this Cl minus will be surrounded by hydrogen of the water. And there are 6 of them. H2O, 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 H2O. 6. This is hydrated Cl minus. We are clear about it? These words are clear? So that's the meaning of the hydration. It's exothermic. This is the solubility curve. Okay. Can you check as the temperature is increasing, what is happening to solubility of KNO3? This black line. As temperature goes up, solubility increases. This is endothermic solution. Endothermic. I can explain you this reason behind it once we are going to do chemical equilibrium. At that time, I'll explain you why is it so. So you can see plenty of lines going up. So their solubility is increasing with the rise in temperature. But can you see one line going down like this? This one. So what is happening to solubility here? It's decreasing. So when I take a solid, to this solid, if I add water, it's going to make a saturated solution, which is like an equilibrium. I'm getting the solution. If I write heat on this side, so what kind of solution making is this? Endo exo? Exo. Now in this exothermic solutions, heat is released. So when heat is released, what happens to the temperature? Temperature of the solution increases, right? If you increase the temperature, it will push the reaction in this direction because already so much heat is there. So I'll explain you more properly once we are done with chemical equilibrium. Right now, you just see that if there is an exothermic reaction, heat is liberated. If you further raise the temperature, it will push the equilibrium in the direction of the solid. So what is happening to solubility? Now, when it is pushed in the direction of the solid, decreases. You're understanding this, children? For exothermic. But if I give you something like this, the solid, I have taken the solid, I'm adding water, and then I have to supply heat also to make it soluble. I'm heating it like sugar in water. You heat it, it's more soluble. It's going to set up an equilibrium and the solution. Now, which side more temperature, more heat is there? Which side? This side, the solid side. So when I increase the temperature, it will push the equilibrium away from heat. So which side the equilibrium will go? In the direction of the solution. So what happens to the solubility? Solubility will increase. So please understand all these lines which are going up, they are representing an increase in the solubility with the rise in temperature. And they don't have the same solubility because they are different. Their lattice enthalpies are different. KNO3 is different. NaNO3 is different. So they have different lattice enthalpies. They have different hydration enthalpies. So you can see the solubility, which is defined as grams per 100 gram. This one is different for them. So can I ask some questions based on this graph? If I give you KNO3 and NABR, which one is showing you more solubility, more rise in solubility with the rise in temperature? Please answer this question, all of you. Mayank, you are there? Yeah, good. Amodita, KNO3. If I say the temperature is this, what's the solubility of KNO3 and NO3? Is it same, different? What is it? Okay, now I'm changing my question. Which substance shows you dramatically decrease in the solubility with the fall in temperature? Dramatic decrease in the solubility with the fall in temperature. Decrease in the solubility. Fall in temperature means move in this direction and move down. KNO3 is the answer. KNO3. KNO3 is showing you, sodium sulfate is showing you increase. This is increase. Increase in solubility with the fall in temperature. It's exothermic solution making, exo. This one is also exo. Heat is released. So these type of questions can be there. They will give you this diagram and they will ask multiple questions. Right? Okay. This solubility curve can be used to separate the mixture, which I'm going to explain you in the next class. But right now, let's do this one. Do we have time to finish this topic? No. So I'll discuss from here in the next class. Solubility of gases. Okay, these things are very important for your chemistry Olympiad and for general understanding of the chemistry. So I see you in the next class. Please finish your unit 2 today. Okay, yeah, children, I have seen many of you are doing quizzes when I'm teaching you. So do you think what I'm teaching is not worth listening? Akash, do you think so? Don't you think that I'm teaching you some new things? I know that half of the things you know, but I'm teaching you many new terms, many new things, a new way of looking at the concept. Okay. No, Akash, but you are very smart. You're very smart. You must be doing on your own whatever you are doing, but that's what needed. Akash and Mayank, you know, they are self-motivated children. Amodita and Anaya, you're also. But my request is when I'm teaching, keep practicing with me because I'm also doing plenty of questions. And I'm teaching you some new language, new words. Okay. So see you in the next class and I'll submit your results today. By tomorrow morning, you will get your results. See you then. Bye bye. Bye. Yes, you can resubmit it if you want. You can do another attempt if you want, right? Doing question multiple times. This is a practice center. It's not something. Uh, okay, unit two. I don't think unit two. No, because unit two I have limited questions. Unit three, yes. For unit three, you can have multiple submission. Unit one also multiple submissions. Yes, yes. You can do the quizzes 1,000 times, Akash. So how I'm going to declare the result? Because most of you are very good in doing the quizzes. So I see that whoever is doing the best. And I'm not counting multiple times. If you're doing a quiz 10 times, I will take the score which is the highest. Okay. See you then. Yeah, I'll correct them, Akash. I will correct them. And Akash, you are doing really good. I'm very happy with you, Mayank, and Amudita and Ananya. Last year, I have a group, and it was very troubling group. I'm really very happy, and I feel blessed that you children are with me. So work hard, okay? See you. Bye.